Okay, so let's try to prove a theorem that I just mentioned at the end of last video, that we saw that it was true for the relation modulo 3, that we had a whole bunch of repeated equivalence classes relation classes, and we also showed that the intersection of a whole bunch of them were the empty set. So let's try to prove this theorem. So if we have any natural number, we're going to let a and b be in the integers. If a is congruent to b mod n, then the relation classes are going to be the same. Also, if they're not equivalent, so if a is not equivalent to b mod n, then the intersection of these two is the empty set. So we're going to take a look at the proof of the first part here, that if a is congruent to b mod n, then a equals b for these relation classes. So we're going to assume that a is congruent to b mod n. All right, that's great. Now we're trying to show that this is true. So we're trying to show that this relation class is equal to this relation class. Now we're trying to figure out, how do I do that? Do we have any type of proving abilities? Well, the question we need to ask ourselves is, what are these? Right? What is this and what is this? What structure do they have mathematically? Well, this is a set of elements. Right? This is the set of all the elements that are related to A, and this is the set of all the elements related to B. So if we're trying to prove that these two sets are equal to each other, well, we need to show that they are subsets of one another. So we're going to prove subsets in both directions. So to prove that this is a subset in this way, we're going to let x be an arbitrary element in here. So we could say let x be an element of the relation class of A. So now if we have an element in the relation class of A, we'd like to figure out, why is this in the relation class of B? Well, to do that, now we need the definition of what are these relation classes. So since x is an element of A, or the relation class of A, we can now say, okay, what does that mean? Well, that means that x is going to be congruent to A mod n. So let x be an element of this. This implies that A is equivalent to x mod n. So if we have this definition of what does it mean to be in this equivalence class, this is what we're saying. Now notice that this is the correct order as well, that A is congruent to x mod n. This is what the definition said. But we're going to actually flip these two. So we can say now, by symmetry, x is congruent to A mod n. All right. So we have x is congruent to A mod n. Now, why is that? Why are we doing that? Why do we need to switch these two? Well, because our goal is to show that x is in this. That means we have to show that b is equivalent to x mod n. So if b is equivalent to x, we have to be able to get b present. Well, the only way that we can connect x and b is having this with this. So since A is congruent to B mod n, and x is congruent to A mod n, by transitivity. So these properties that we proved about the relation of congruence, we had that they were symmetric, right? We were able to switch these. And by transitivity, that if A is congruent to B and x is congruent to A, or in other words, really maybe the order that you think about this is x is congruent to A is congruent to B, that means x is congruent to B. So by transitivity, x is congruent to B mod n. But if we're trying to use this definition, we need to be able to switch these two sides, because we said if x is in the relation class of A, that means A is equivalent to x mod n. This doesn't quite show what we want. We want to switch these two. So then by symmetry, B is equivalent to x mod n, which implies that X is in the relation class of B. So this proves the one direction of the subset. Now, if we're trying to prove the opposite direction over here, we would start out with X is now an element of B, but this is almost exactly the same proof. The only thing that's a little bit different is that we had this assumption that A is equivalent to B. We would end up using the fact that B is now equivalent to A. We'll use symmetry a few more times, but basically the proof is almost identical to this. So there's really no point of doing this. So this is nearly identical to the other direction. And that concludes our first part of our proof that says that if A is congruent to B mod n, then these two relation classes are going to be equal to each other. So now we'll take a look at the proof of the second part. So we'll try to figure out, how do we know that if these two are not equivalent to each other mod n, why is it that we have the intersection being the empty set? So why is there nothing that's going to be in both of these sets? We saw the example. How do we prove this now? Well, obviously we're going to start out with the assumption here that A is not congruent to B. So we will assume that A is not congruent to B mod n. So to show that nothing's in the intersection, one of the strategies that we can do is we could do something like a contradiction. Right? We're saying, what if it isn't empty? What if there is something that's in both of these? How do we get something that's not true to appear? How do we get some type of contradiction? So we will say, suppose to the contrary that there exists some X that's in the intersection of these two sets. So what if there is something in there? We'd like to show that this is going to lead to a contradiction. So if you are in both of if you're in the intersection, that must mean that X is in this and X is in this. So then this implies that X is an element of the relation class of A and X is an element of the relation class of B. So we're just using the definition of intersection to now be able to prove, or be able to separate this into two different statements. So if X is now an element of A mod n, or X is an element of this relation class, this is what it means. We said over here that this implies that A is congruent to X mod n. So then, furthermore, this implies that X, or that A, is equivalent to X mod n. And now by the same statement over here, that if X is in the equivalence class, or in the relation class of B, then that means that indeed B is going to be equivalent to X mod n. And B is now equivalent to X mod n. All right. Now, again, we're trying to come up with some type of contradiction. How do we come up with a contradiction? Well, what we've said here, A is congruent to X, B is congruent to X. So hopefully, if you're thinking about what do we know about congruences, we can use something like symmetry at this point, right? So this implies that this, using symmetry, we would like to now come up with one of these to switch. So I could now switch these two. So by symmetry, we see that X is congruent to B mod n. Now, we have to be careful that we do want to state this fact, that by symmetry this is true, because it's not true for every relation. There could be lots of relations that don't allow us to freely switch these. So if we define congruence in a very wonky way, I can't just always freely switch these. So make sure that you're stating by symmetry, because that's the only reason that we can switch these two. So now that we have that A is equivalent to X and X is equivalent to B, we can now state that A is equivalent to B. Why is that? Well, because of transitivity. So by transitivity, A is equivalent to B mod N. So we have these two, implies this one. Well, obviously, we now have the contradiction, right? Because we said that we assume that A is not equivalent to B mod N. Now we've just shown that A is equivalent to B mod N. Those two cannot simultaneously be true. So therefore, we have a contradiction. So this is a contradiction, since we said that A is not equivalent to B mod N. So if it's a contradiction, what that means is that there is no element X that exists, that X doesn't make sense. So hence, the intersection of these two equivalence classes is the empty set. So that means that there was no element there to begin with, and now that concludes our proof of both of these statements. So for a general N, we have that if these two numbers are equivalent to each other mod N, then their equivalence classes, or the relation classes, are the same. If they're not equivalent, then these relation classes are going to be distinct, that there's nothing in common with both of those.